Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. In last lecture, I showed you how to tackle double or a triple bond in order to get carboxylic functional group. And in this lecture, we're going to go through alcohol and also we want to see whether we can actually get carboxylic by starting with aryl alkyl molecules. We know from previous chapter that we can use a strong oxidizing agent like a chromic acid in order actually to take a primary alcohol and turn it to a carboxylic group. This is really strong an oxidizing agent, and it will take the primary, it will turn it to aldehyde, and then the aldehyde will go through another step of oxidation, and at the end it will turn to acid or carboxylic acid. And so the reaction is not going to stop, stop by the aldehyde as a final product. And in case of secondary or say tertiary alcohol, the secondary alcohol, it will turn to a ketone, and it will stop there. And tertiary alcohol, it will not get involved in this chemical reaction. And so, as you see, in this case, we have a secondary alcohol, and that secondary alcohol, it will go through oxidation. It will give us a ketone. Now, I can use mild oxidizing agent, but the mild oxidizing agent, it will give me only aldehyde or a ketone. It depends what I start with. And so, for example, if you go with a PCC or pyridinium chlorochromate, that's going to take the primary, and it will turn it to aldehyde. And in case of secondary, whether you're using a harsh or mild oxidizing agent, product will be just a ketone technically. And we have such a molecule that it has a couple of functional groups. The one on the left is a secondary alcohol. How do I know it's a secondary alcohol? Because I have a carbon that attached to two more carbons. So I'm going to call it secondary alcohol. And here we have a carbon that is attached to only one carbon and is neighbored with another carbon. And so that's going to be a primary. And then the one on the right side, we call it aldehyde. And I already put the label for them, so I'm not going to write it again. Now, when we run oxidation, it depends on whether we are using harsh oxidant or mild oxidants, we get a different product. In this case, we are using chromic acid, which is a harsh oxidant. That means if it's possible, it will take a primary alcohol, it will turn it to acid rather than aldehyde. So we said the primary, it will turn to acid by harsh oxidant, and then secondary, it will turn to a ketone. And if you have aldehyde, you can oxidize it and turn it to acid. And again, is it possible to oxidize the ketone? No, this one is not going to happen. So the product that we're going to get, it will be something like this. And so as you see, the aldehyde turned to acid. Well, the primary here, first it will be oxidized to aldehyde, and then it will go through another step of oxidation, and that's going to, again, it will give us an acid functional group. But the secondary alcohol, it will be oxidized just to ketone, and it will stop there. Okay, so this one turned to ketone, that one turned to acid, and last one here we have a primary that got oxidized and turned to carboxylic acid. So that's another way actually to create a functional carboxylic functional group. Okay, now I'm going to tackle some aryl alkyl and see whether actually I can get carboxylic group by using those compounds. If you go with permanganate and you use it like with like a basic in a basic solution, and also you are applying heat. So I'm going to say I will add the sodium hydroxide or base to it, and then I'm going to say heat. Why do I apply those actual condition? Because I want to make the oxidant stronger and stronger in order to oxidize anything to the extreme case and last step that is possible. And the way you're going to actually assign the product, you will find the first carbon that attached to the benzene ring or the phenyl ring, and that carbon you're going to call it benzylic carbon. Benzylic carbon or benzylic position. Now, ask yourself, do I have hydrogen attached to the benzylic carbon? Okay, so I'm going to say look for H atom attached to benzylic carbon. Okay, look for that one. If the answer is yes, then you will oxidize that carbon and you turn it to carboxylic acid. So product in this case, it will be this. I will get rid of the hydrogen and replacing them by COOH. Okay, and now if I highlight any benzylic position, I can see it, and I can see in some cases I have hydrogen atoms, so it's possible to oxidize them. But for example, for this molecule, we have methyl groups there, so that's not going to happen. And for this one, I'm going to say no reaction, because I don't have any hydrogen attached to it. But the rest, all they do have hydrogen atom, at least one hydrogen atom you can find there, or two of them. So it's possible to have oxidation. Okay, quick question. What if I have only one hydrogen atom, just one hydrogen atom attached to the ring? Is it possible? An example is this. Imagine you have such a molecule. Let me draw it in another page. Is it possible to oxidize such a molecule? Isopropyl. Isopropyl, it has only one hydrogen, the rest are CH3. Is it possible to oxidize this one by permanganate? And the answer is yes, you can oxidize it because there is a hydrogen attached to the benzylic position. So this one, simply, this carbon is going to get oxidized and it will turn to COOH. So the answer is yes. If there is hydrogen atom there, you can oxidize it. Let's go back to the example I mentioned. And I want to tackle this one. In this case, we have two benzylic positions. So what will happen? We're going to chop the molecule from here. We're going to chop it from there. And we will get such a molecule, benzene ring, that it has two carboxylic group. And they are in ortho position. And the last one is like you have just a long chain. And again, it doesn't matter. You can cut the molecule from there, and that's going to give you benzoic acid. Okay, and here are the answer for all of them. So as you see, in all example that we had benzylic position, benzylic carbon with a hydrogen atom sitting on them, we managed to oxidize those molecules, except this one that is attached to 3 methyl groups, so there was no product there. There are other methods to use in order actually to get carboxylic acid, and we can talk about hydrolysis of nitrite, or we can actually use a Grignard reagent and react it with CO2, and that's going to give us carboxylic acid. Okay, let's practice some of them. And in this case, we have cyanide, and cyanide is going to behave as a nucleophile. So this is going to be the nucleophile. The nucleophile will attack benzylic carbon, and that benzylic carbon is more capable of handling positive charge. And so in this case, it's going to be because it's the primary. It will go through SN2 reaction, and simply it will let bromide to leave the system. So the intermediate, intermediate that we get, it will be this C attached, or I should do a better job than this one. I'm gonna let me draw it here. So our intermediate, it will be this. We get carbon attached to nitrogen through a triple bond. And now this one, it can go through hydrolysis. And the hydrolysis is providing acidic H. And we know nitrogen, it has a lone pair. So first thing that's going to happen, and nitrogen will get one hydrogen, or H+. If that one happen, if nitrogen goes after H+, and very soon, we will have a carbon with a positive charge. Remember, nitrogen still, it has a lone pair. It can, share it with carbon in order to stabilize it. Okay, but normally carbon is going to have a positive charge. The time to add the nucleophile, and what's a nucleophile? It is going to be water. And now water, it will go after carbon. And if that one happen, we will get this product. Okay, and if you take an H from it, say minus H, how? Just simply, we have another water molecule. That water molecule is going to go after the acidic H, and it will go after this acidic H, and it will take it out of the system, and it will give us such an intermediate. Okay, I'm going to erase charge from it, sorry, hydrogen from it, and so this hydrogen now is gone. Now the hydrogen is gone, I can put 2 lone pairs there. Okay, and so as you see, we have a lone pair in nitrogen. There is a double bond, so we can't technically have a rearrangement there. Well, maybe the oxygen can share, can share actually a lone pair with carbon. And if that one happen, if this one happen, then very soon this double bond, it will move on nitrogen. What does it mean? It means nitrogen is going to have negative charge. And if nitrogen has a negative charge, it's capable of accepting another H plus. So it can accept another H plus because the solution is acidic. And so very soon nitrogen is going to go after this one. And what do we get? We will get this product. Okay, the product that we're going to get, let me shrink this one. So we're going to have another H, this M attached to that nitrogen, and the cost for it, this bond now is gone, and we're going to get a positive charge on carbon. Now, from now, because still we have, like we have nucleophile, and the nucleophile is water, we can add another water molecule actually to that carbon, and if that one happen, you might get this molecule. So now we're going to have water molecule attached to this. That's going to be something like that, positive charge. And of course, this one is going to here, again, we're going to subtract H plus from it. And if we subtract H plus from this one, how do I subtract H plus? Just simply the solvent or water will take actually that H plus. So I can say I have water is going to go after this H, and it will give me this product. Okay, I got such a molecule. And now I know nitrogen is more basic than oxygen, and the solution is acidic. What if we add another mole from acid? Another mole from this acid, it will protonate nitrogen. But the second you protonate nitrogen, now you will have a positive charge on nitrogen. And now that you have a positive charge on nitrogen, nitrogen will turn to a good leaving group. And so I have a positive charge, and entire of this piece is going to be a good leaving group. And now, how do we kick the NH3 out of the system? One of this nitrogen is going to, one of this oxygen atom is going to share a lone pair with carbon in order to kick nitrogen out of the system. And if that one happen, we will get this molecule. Okay, so I'm going to move entire of this one. This one will move out of the system. It will move as, say, NH3. And now we have a double bond there. Okay, this one, it has a positive charge, so that's going to go through rearrangement, and the rearrangement, it will give me this. So if water gets involved again, water is going to go after this acidic H. It will take that H out of the system, and it will give me this molecule. So I got carboxylic acid plus hydronium ion. Now, what will happen with NH3 or ammonia? Remember, the solution, our solution is acidic. Okay, and as you see, I showed that we do have hydronium ion. And so NH3 is not going to stay as it is. In fact, this one is going to react with hydronium ion, and it will get extra hydrogen, and it will turn to NH4 with a plus charge. Then we get H2O. So the final product, if you want to really highlight them, the two final products, there will be these two. You will get NH4 plus and also a carboxylic acid in an acidic solution. Those two are going to be the product. And this is going to be the end of this lecture, and thank you very much.